Last year I asked myself a simple question. Could I design a remote controlled blast gate that even somebody with no electronics background, no soldering experience, and no coding knowledge could make for their own workshop? And honestly, I think we've achieved that. So many of you have downloaded plans, built your own versions, made your own modifications, and really made this project your own. And while I think this solution works, and it works pretty well, it barely scratches the surface of the potential possibilities that such a system could become. Because once you start thinking about automation, when you start thinking about wireless control, you start to ask all sorts of questions like, well, what if? And you realize that there's an entire chapter that we haven't explored yet. So today we're once again revisiting this project, and we're going to see what it's going to take to turn this remote controlled project into a fully autonomous solution. So the original system was designed to be as simple as possible, using off-the-shelf components, minimal wiring, basically no coding whatsoever. Just press a button and the gate opens, and press the button again and the gate closes. And it worked, and it still works, and I use it every day in the workshop, and I genuinely love the solution. But the more I've used it, the more I've realized something. We're really only solving half a problem here. We're really only scratching the surface of what a system like this could potentially do. Because once you start thinking about automation, proper automation, we start to realize the limitations that this actually has. The electronics I used in the original iteration of this project were about simplicity, not scalability. It was never designed to really grow, and it was never really designed to be smart. And if we want to take this to the next level, we can't really add to what we already have. We kind of need to take a step back and start again with a clean slate. Now, before we jump straight into it, it's important, at least for me, to set a list of goals or criteria that we want this new system to achieve. And actually, a lot of what I'm about to outline comes from you. Ever since I started this project way back last year, so many of you have reached out via email, via messages, social media, etc., sharing your ideas, your suggestions, your experiences and expertise in this area. And I've definitely taken a lot of that information to heart, and a lot of what I want to include in this particular system isn't just for me, but it's actually also for you. I've often said that my projects start with me solving a problem for my needs only, and then sharing it with the rest of the world, and if it's applicable to them, well, great. But this project's very different. This one won't be just about solving my problems, but it'll also be about, hopefully, solving a lot of your problems as well. So let's get stuck into the criteria we're going to set here. So requirement number 1, remote control still does matter. Yes, we are exploring automation, but we definitely want the basics to still work. Not every gate in my shop is going to have a machine attached to it, so it's important to me that I'm able to still control those manually and open and close them when I want to. Now, the current system, which uses the Bamboo Labs CyberBrick platform, that's limited to 2 gates only. So obviously we're going to have to change that to allow a lot more gates to function on this system. So we want more gates, more flexibility, but still keep it simple with the ability to control with a remote. So requirement number 2, the system needs to be able to respond when I turn a machine on. If I turn on a machine, the blast gate associated with that machine should open. And any other gates in the system that are relevant to the functionality of this particular gate should also open, or alternatively, they should close. And this is the big feature that everyone has been asking about, automation when we turn on a machine. So ideally, we want to implement some smarts in the system to allow it to understand when a specific machine is turned on and appropriately open and close the gates relevant to that particular machine. So requirement number 3 is pretty obvious. If we're going to automatically open all of the gates relevant to a particular machine, we want to be able to turn the dust collector on at the same time as well. Because obviously opening gates without the extractor turning on is kind of meaningless. And when we talk about full automation, we want to include the dust collector as well. Which then leads to criteria number 4, which is once we're finished with the machine and we switch it off, we want the dust collector to run for a certain amount of time and then switch off. And then once that's done, the appropriate gate attached to that machine should then close. So in other words, clean, automatic, no intervention required, only working with the machine itself. Dust collection handles itself. So to summarize, we want remote control access when we want it. We want automatic control when we don't. We want automatic dust collection. And if we can achieve all of that, I think we're going to have quite a system on our hands, which means there's nothing left to do but to start designing and building. So the first place to start is by visualizing the system as a whole and identifying the core components we'll need to build, and more importantly, how they're all going to interact with each other. So let's imagine a real-world scenario. We have a machine, which in this case is my thicknesser or planer if you prefer. When the machine is turned on, a power detection module attached to it is going to sense that the machine is drawing power, and this module is going to send a wireless signal to the receiver connected to the appropriate blast gate telling it to open. Once the gate opens, it's going to send a confirmation signal back to the system to say that the airflow path is ready. It's also at this point that the power detection module can send a signal to any other gates that should be opened or closed. And then once everything is in the correct state, we're going to send a signal to the dust collector, which in my case is going to be connected to a wireless power switch. So in summary, there are really two main modules we need to design and build here. The first is going to attach directly to the blast gate, very much like the previous version did, but this time it's going to need some additional capabilities. It still needs a wireless receiver and transmitter of some type, so it can communicate with the rest of the system. And of course, it still needs to control the servo motor accurately to open and close the valve. And it also needs to accept manual input, either from a remote control or from a local override if we want to change the gate's position directly. Now for module number 2, and this is where things are going to start to get a little bit more interesting and probably a lot more complex. First, it needs the ability to detect when a machine is turned on and when that machine is turned off. Secondly, it's going to need two-way wireless communication so that it can coordinate with the rest of the system, particularly the blast gates. And finally, we're going to need to work out a way to communicate with the dust collector itself, allowing it to turn it on and of course turn it off when required. Now, of course, that all sounds fairly straightforward, but there's only one problem with this plan. I have no idea how to do this. So don't go anywhere, I'm going to be right back. This shouldn't take long.
Several months later.
So welcome back. While it's only been a few moments for you in the intermission, it's actually been about 3 months for me here. So it's taken well over 3 months now of design work, prototyping, and a lot of testing to now get to this stage in the project. But the net result is that I think we have something now that is leaps and bounds ahead of the previous system in terms of functionality and performance. And what I have here are the two final versions, or at least the final versions for now, of the core modules that we set out to make at the very start. So module number 1, which I'm calling the gate module, I guess, or servo control module, this is going to attach directly to our blast gate. And our second module, which I'm calling the power control module, this is going to connect to a machine and it's going to tell us when a machine is turned on and when it's turned off. Now on the surface, these modules look pretty straightforward. The control module for the servo looks very similar to the original one. But under the hood, there's quite a bit going on in these two modules. So what I want to do now is walk you through how these work, talk a little bit about some of the design decisions I made, and assemble one of each so that you can see how they're made and some of the components that are involved in construction. So it's probably a good time to do a bit of a disclaimer here. Now, I'm no electrical engineer or electronics expert by any stretch of the imagination. So everything that you're seeing here is based on my own experimentation, my own research, my own testing, and my own trial and error. And if you're looking to build something like this in your own workshop, then it's very important that you do your own due diligence. Do your own research. If you're not comfortable with working with electronics and power systems, then please make sure that you reach out to people who are. Because anything related to electricity, of course, carries some danger, and we need to make sure that we're doing things safely. So to begin, I'm going to attach the servo to the servo mounting plate. Now, if you've been following along this project, you'll know that originally I've been using the smaller micro servos. And while those can work, these are the 5.1 kilogram torque servos, and they perform a lot better for this application. So they've become the standard for the design moving forward. I'm going to have links to all the hardware that you need down in the video description. The servo simply screws into the 4 mounting points in the plate. We can then set this to the side. This is the new electronics closure that mounts to the gate, and the first thing I'm going to do is install the power barrel plug. This is a 2.1mm barrel plug with screw terminals, and this is going to accept our 12-volt power adapter. I use a dab of super glue here to secure it to the enclosure. Next, I'll attach a toggle power switch to enable us to turn the power on and off at the module. The switch that I'm using here actually comes from the same Cyberbrick kit that I used on the original gate designs, so I'm going to repurpose these for this one. I connect this to the barrel plug and then screw this into the appropriate spot using another M2.5 screw. Next, I'm installing an override button. This button will enable me to override the gate position directly should I need to, and will serve as a final fallback just in case. So the next component to go in is called a buck converter. Now the job of this component is to reduce the 12-volt power that's going to be coming in down to 6 volts, which is what the servo motor needs. If we don't reduce the power input, we'll fry our servo motor, so this converter is important. I've already pre-configured this converter down to 6 volts, which is achieved by turning a small adjustment knob on the board and testing with a multimeter to make sure it's outputting the correct voltage. I've also already pre-soldered negative and positive inputs and outputs onto the board. This is actually the only part of the whole project that you'll actually need to solder anything. The last part for the power switch is to connect the other terminal end. This will eventually connect to our power splitter, but for now it's going to remain unconnected. Next are the status LEDs. These LEDs let us visually know the status position of the gate, so red for closed and green for open. These are 5-volt rated LEDs. This is a distribution board, and its job is to tie in all our grounding and 5-volt connections to our microcontroller, which we'll discuss later on. Think of it like a power board. Anything that's attached to it shares the same connection. Now that the board is in, I'm going to clean up some of the wires, specifically the negative wires, and connect them all to the same side of the distribution board, as these all need to be on the same ground. None of these need to specifically go in any specific spot, just as long as they're all on the same row. Next, I'm going to be splitting the power between the buck converter and the microcontroller. I use this small screw terminal block that I've cut down to 3 sections. I'll screw in the positive of the power button and the positive from the buck converter, and eventually I'll connect this also to the microcontroller. Effectively, it's just acting as a junction. Now the last thing I'll do before I put the microcontroller in is to add some spacers or steppers. This will raise the controller board above our terminals, and I bought these as part of a kit. Again, I'm going to link to all of the components that I bought in the description. This is what's called a shield, and it's what our microcontroller is going to plug into. The shield's job is to distribute the connections from the microcontroller into terminals we can attach our wires to. It is optional, but it makes our life so much easier. This screws directly into the risers we installed before. With the shield in place, we can now start to plug in our data wires for our components, such as the LEDs, the wireless transmitter and receiver, and the servo. These are effectively the wires that let our microcontroller talk to and control our components. Now, the specific locations you need to plug these into are really going to depend on the code you implement into your microcontroller, and I'm going to go into more detail regarding that later on. It's time to finally install our wireless transmitter and wireless receiver. This is a standard 433 MHz RF transmitter and 433 MHz RF receiver. It's the type of technology you'll find in things like your garage door. It's a well-established standard, but it's worth very quickly talking about this in a bit more detail. It's worth pausing for a moment to very quickly cover the wireless technology that we're going to be using in this particular project and why. Now, when I first started scoping and designing for this project, I had available to me all sorts of different types of wireless technology. We could have certainly gone back to using what we used before, which is Bluetooth technology. We could have used Wi-Fi, or we could have used any of the other consumer grade wireless standards that are available. Now in the end, I've opted for what's called RF433 megahertz. It's a wireless standard that you'll find very common in your home, especially, your garage doors and things like that. Now the reason why I'm specifically selecting this standard is for two reasons. Reason number one is that we want to maintain some sort of compatibility with some of the other hardware components that we're going to need to interact with. Now, one of the criteria that we have is that we want to be able to turn the dust collector on and off. And the way that we're going to be doing that is using these wireless power gates. Now, these work on that same 433 megahertz standard frequency. So it makes a lot of sense for our wireless transmitter and wireless receiver that we use in our system to follow the same standards. And it also means that we can tap into remotes that use that. So off-the-shelf remotes like this one that I particularly bought for this particular project work really great with it. Now, it's really important to note that in many countries, there are rules and laws regarding how you use this particular wireless technology. So make sure that you double check your local governing body to make sure that if you do implement something like this in your workshop, that you're meeting all of those particular requirements. Right, so I've connected our receiver and transmitter to our case, and I simply tuck these into the enclosure. It's worth mentioning that if your only objective is to open and close the gate with a remote, then you really only need the receiver. You don't need the transmitter as well, since it doesn't need to broadcast any status back to any other device. We are now finally ready to connect our servo to our electronics. We need to connect the power from the buck converter, the ground or negative to the shield, and the data to the appropriate pin. It's finally time to install our last component, which is our microcontroller. But before we do that, I've mentioned microcontroller a few times in this build video so far, but we haven't really talked about which one I'm using and more importantly why. Now, just like the wireless standard, there is quite a few different microcontrollers we could use in a project like this. Which one you choose really comes down to what you need your system to do. So when I was scoping this, there were three clear choices when it came to microcontrollers. Those were the Raspberry Pi, the ESP32, and the Arduino. Now the Raspberry Pi is incredibly powerful, but it is closer to a tiny computer than it is to a microcontroller. It can run a full operating system, so it's fantastic for really complex projects, but for builds like this, it's probably overkill. Which also adds to the cost. So one of the things that we want to try and do is keep this as cost effective as possible. So while the Raspberry Pi is absolutely an option, and I've seen some people use it, it's just not the right one for this one. Now, the other one that's really interesting is the ESP32 microcontroller. It's extremely capable and actually has Bluetooth and Wi-Fi built into it. And for a lot of automation projects, I can see that as being a really fantastic choice. But in this case, we already kind of ruled out that we don't need Bluetooth and we don't need Wi-Fi. So it adds cost to the particular controller for two things that we're just not going to use. And again, I have seen people who've used that controller to great success. But again, I just don't think it is the right one for our project. Which leads us to the last one, which is the Arduino. Now the Arduino was the logical choice because A, it was very cheap, very cost effective. It powers up or boots up pretty much instantaneously, has a plethora of accessories and things that we can attach to it. So it's more than capable in handling our servo motor, our LEDs, our RF controllers, and more. And in fact, one of the best things about it is that it's an open source platform, meaning that there are dozens and dozens of clone brands out there, all very cost effective and make it a very good choice in this particular project. So in this build, the Arduino actually is the perfect fit. So our chosen controller is the Arduino Nano, and it plugs directly into our shield like so. So before we can test this, we need to load our program into the Arduino Nano. To load our program into the Nano, we simply plug it into our computer using USB and upload the software, or firmware if you prefer, into our controller. Now I am going to go into more detail later on regarding programming, but for now we just want to load our code into the controller and to test to make sure everything's working. To test, I'm simply plugging in our 12-volt adapter, and then I'm going to check to make sure that the servo moves, that the override button works, and that it responds to our remote. With it working, we can package it all up with the servo ready to install in our gate. And there we have it, our finished module. Installing it onto the gate is simple. A few MX6 bolts secure it, and the servo arm slots into the servo arm housing. Once that's done, we can do a final test. With the electronics for the gate module now finished, let's switch over to the power detection side of the system. The detection system is actually made up of two parts. One module is responsible for sensing when a machine is drawing power, and the second is the control box that manages communication with the rest of the system. And the starting point for this is something pretty simple, a humble extension cable. Specifically in this case, I'm using a Y-split cable because I have two machines, my thicknesser and my jointer, that both connect to the same blast gate. Now obviously I won't be running both machines at the same time, but using a split cable means I only need a single power detection system for this gate. What I'm doing here is carefully removing a small section of the outer casing from the cable. I'm not cutting the cable itself, just scoring the insulation enough so that we can peel back a section of the outer sheath and expose the three wires inside. The key here is to be very precise. We only want to remove the outer jacket without damaging the wires underneath. So take your time on this step and be very careful not to cut the conductors inside the cable. Now what I have here is called a CT clip or current transformer. It's a non-invasive way of detecting current, which means we don't have to cut into the wiring or make any electrical connections to the cable itself. Instead, the clip simply clamps around a single conductor, in this case the live wire, which is the brown one. When current flows through that wire, the CT clip detects it, allowing the system to determine when the machine has been switched on. I've also designed a small enclosure to house the sensor and the wiring, so everything stays protected and there are no exposed wires. Now for the control module. The core component inside this box is the AC current detection module. This is what the CT clip connects to, and it's responsible for translating the current signal into something the microcontroller can read. From there, the microcontroller can determine whether the machine is drawing power, or in other words, whether it's turned on or off. And this module, of course, is going to include an RF transmitter and an RF receiver, so that it can send commands to the blast gates around the shop, but also receive status updates back from those same gates. And it's also through this same communication system that the module is going to trigger the dust collector to turn on or off. So this is another distribution terminal, although much smaller than the one that we used in the gate module. Just like before, this is going to act as our 5-volt distribution rail, and it's also going to act as our grounding rail. From here we'll power the LED, the AC detection module, and the wireless transmitter and receiver. Now I know I'm kind of powering through some of the details regarding where wires go, but I'm going to include a full wiring diagram and schematic with the files. And finally our nano goes in. We can then tuck in the transmitter and the receiver, as well as connect our power source, which is going to be a USB cable. And then finally we can secure it all with a couple of M2.5 screws. And that's it. Our power detection module is now complete and ready for testing. So this is the part of the video where we kind of have to pause and address the elephant in the room, which is programming. Up until this point, everything that we've built has been completely physical. We've mounted the servos, installed all electronics, and wired everything that makes up the system. But right now, it doesn't actually do anything yet. It's really just a collection of hardware that's waiting to be told what to do. And that's of course where programming comes into it. Now, I'm not going to lie, programming is probably the most important part of this project and easily the most complex part of this project. I actually have a background in software engineering, so programming is not something that's unfamiliar to me. But even with a foundational knowledge in programming, I found this to be an exceptionally challenging and complicated part of the process. In fact, I probably spent close to 2 months on just the programming alone. Testing, debugging, and trying a whole bunch of different approaches until I got the behavior that I was looking for. Now, the good news is that I absolutely believe that it's within the realms of possibility for anyone to do this. You don't need to be a professional programmer to start getting results with a system like this. Even relatively small programs with just a few lines of code can be sufficient enough to at least control inputs, outputs, servos, motors, and more. So the complexity of the programming really depends on the complexity of the system that you want to build. Now, obviously, we've aimed quite high here. We have a lot of gates and we have a lot of automation that we're trying to achieve here. But if automation really isn't your thing and all you'd really want is just to be able to remotely control gates, just more of them, then the code to do so, I believe, is relatively straightforward and very approachable for most people. Now, the logical question a lot of you will be asking is, Anthony, if your code is working, why can't I take that and just simply put it into my system? And the answer is you absolutely can. I will be including my code in the updated files that I release. However, using my code is really only going to be a starting point for you because there are several reasons on why that isn't quite that simple. Now, one of the reasons is that code like this is generally specifically written for the hardware it's connecting to. Things like which pins the components are connected to, the servo motors, how the wireless is configured, and the signals that each module is expected to receive, all of that gets defined in the code. Even relatively small changes in hardware can mean that you need to update or modify your code. For example, these wireless remotes that I'm using for the system, they transmit their own embedded signal codes whenever a button is pressed. These signals need to be captured first and then programmed into the system to allow the microcontroller to interact with them. And the problem is that, for example, even though I have two identical remotes here, they're bought from the same vendor, they are the same brand, same model, same everything, the codes that they generate when we press a button are completely different from each other. Meaning that even though they are the same controller, they don't send the same codes even for the same buttons on each. Which basically means we are having to pair the remote with the particular software or the system that we're using. Meaning that if you were to simply take my code and paste it into your controller, and even if you bought the same remote, the odds are very strong that it will not work because you need to capture the unique codes that these are generating and then insert those into the program. And the same thing extends to our wireless power adapters. These adapters have their own internal codes, and even if you have the same brand of power adapter, there's absolutely no guarantee that the codes that they're looking to use are the same as the ones that I'm using. And one last thing I'll mention about wireless power adapters is that you can't use all types of wireless power adapters. Some power adapters, like this Arlec one that's really available from my big box store, are not compatible with this type of project. And that's because gates like this actually have what's called rolling codes in them, meaning that the on-off signals that are sent to these types of adapters keep changing even within the same system. So you need to find a power adapter that doesn't use this type of embedded code. Of course, I'm going to leave a link in the description to the power adapter that I found that works really well with this. So basically, where does that leave us? Now, if I compare this project compared to our previous one, which is based on the Bambu Lab Cyberbrick platform, then on a software complexity scale, that one's easily a 1. But for the software complexity scale for a system like this, it's definitely up there with an 8 or a 9. It is much more complex. But the complexity of the software that you need to implement is really dependent on the features and functionality that you want. Like I said, if you just want a simple remote blast gate that opens when you press a button, then that's achievable with relatively little coding. And I'm going to include both types of code in the updated plans that I'm going to release. So they're going to have some basic ones for just opening a blast gate, and it's going to have some more complex ones for an entire system like this one. But it's going to require you to make some modifications or at least replace some of the variables involved with ones that are relevant to the hardware that you end up acquiring. I'm also going to leave some resources to some programming information and tutorials that I found helpful in getting started in this area. The one thing I've learned about this process is that the possibilities are pretty much endless now. When you have the ability to explicitly tell hardware what to do, then it's starting to unlock all sorts of future projects that I might implement electronics into. And of course, if you have questions, comments, queries, or if you want to find out more information, then leave a comment and I'll do my best to answer those or send me an email. Now, with that all having said, let's move on to the more exciting part, which is installing all of the blast gates into the workshop. So it's worth quickly having a look at these gates as I take them out. So these are the original gates in the system. These have been running from day .1, and so many people, ask me how are the gates doing, especially the gates that have the original micro servo. So this is this is actually the original. This is Genesis right here. So this is gate number 1. This is the very first one I ever made, and that I made you to be motorized. So yeah, so as you can see, she's really, really clean. The motor on here still working fine, absolutely fine since day .1. So the action is still very, very smooth, as you can hear. So yeah, working really well, this one still. So I could probably still repurpose this, but I think what I'm going to do is put this on my shelf as a reminder of where this all began. So yeah, absolutely no problems whatsoever in terms of performance. These are relatively self-cleaning as far as I can tell so far. This one's been running for 8 or 9 months. I've never taken it out, never had to clean it, never had to adjust it. So yeah, I think it's pretty good. So the next thing that we're going to do is install our power detection system, and we've got our power detection module from earlier that we made. So let's go ahead and now install all of that. Now the first thing I'm doing is I'm just going to add this power adapter. This particular power adapter has a couple of extra USB ports here, and that'll become obvious in a second on why we need that. So we simply plug that into the socket, and then our power detection module plugs into that. That then, of course, plugs into whatever machine you want to use. Then the next thing that we need to do is install our power detection module or control panel that we made earlier. So this one's designs that you can probably mount anywhere in your workshop. Higher is generally a little bit better. In my particular case, I've just made a couple of hooks, and that's just going to hook onto the back of my workshop here. So you don't have to go too high, but you do have the freedom to mount this much higher. You're really only limited to the length of your USB cable. Now the obvious thing to do next is to power it, so we need to plug it into power. And the last thing that we need to do is to connect the signal cable. So this is the cable that goes from our power detection module, and that goes into our control panel here. So when the power is connected, it detects that and it's going to turn the system on. Now, when we initially plug this in, it's going to detect some signal. Whenever you plug this in, it's going to. So during its initial detection, it's probably going to open the gate behind me, and it's also going to turn the dust collector on temporarily. This is just a way to test that the system's actually working. So if I plug this in, so the power gate just opened, a couple of the other gates opened, and the power and the dust collector is turned on. It should now turn off. Gate closed, turn off. So that's actually it doing its initial boot up test. So once it's switched on, there shouldn't be any reason to switch it off. But certainly this is a good sign. It means that things are working, but we're obviously going to do a proper test in a second. Right, so here we go. You join me at a very exciting moment because we are now doing our first integration testing. Now I've got the camera set up with a wide angle view, so hopefully you can see each of the gates from that camera angle, so we can see how the system is behaving as a whole. So the first thing that I'll be testing are the core basics. So when we first set out the criteria at the beginning of the video, we did say that we wanted things like basic remote control to still work. So I have 6 gates in the shop, each of them programmed hopefully to this particular remote control. So fingers crossed all of these work just like they would have before. So gate number 1 and gate number 2 are attached to the main dust collector, and these two are effectively our old manifold system. So those should work independently still. So gate 1, gate 2, So those are working. Gate 3 is over there. It's going to be connected to our thicknesser and our planer. So both of those run off the same gate. So we only need one of those for that. And let's check to make sure gate number 3 is still working remotely. So that's perfect. Gate number 3 is working. Now gate number 4 and 5. So number 4 is connected to, or will be connected to my drum sander and my bandsaw. So that particular gate is used for those two machines. And checking that its gate works. So gate 4 is working. And the last gate is gate 5, which is connected to my floor gate. So that one is just when I'm sweeping up, it's got somewhere for some of the dust that's on the floor to go. So that's number 5. And that's working. Now the last gate is gate number 6. Gate number 6 is connected to my table saw. So gate number 6, eventually I'm going to modify the code a little bit. So I'm going to modify the code so that when gate number 6 is open, then gate number 2 here is open and gate number 1 here is going to be closed. And that's a little bit about the beauty of this particular system. We now have the base core electronics there. So every gate has a wireless transmitter and a wireless receiver. So we can make modifications to this system to suit our needs. And in this particular case, I want that particular gate to make sure that just those two are closed. Because in this particular case, I don't quite want to connect an automatic blast gate system to it or an automated tool detection system for the table saw, because there's a lot of use case scenarios where I imagine that I don't want the dust collector just to simply turn on if I use that. But I certainly want the gates to align when I am using the table saw. So again, that's part of the flexibility of what we've built here, is that by just changing software, we can actually fundamentally change the functionality. So let's of course test gate number 6. Now you can't see it from here, but I can. And that one's working fine. So now it's time for our power automation test. So what I'm going to do is set up a real world scenario, but I'm going to set up the worst case real world scenario. So obviously the idea is that when we turn on the thicknesser or our particular machine connected to our power detection module, it's going to open the appropriate gate and close all of the other gates that shouldn't be open. So I'm going to configure this in the worst case scenario so that the system has the most number of gates it needs to turn over. But this represents a worst case scenario because we need to impact or change the status or the current configuration of not just 1, 2, 3, 4 and 5 gates. So 5 gates total need to change its orientation. And we want the system to be able to automatically detect that and close the appropriate ones and open the appropriate ones. Now the only thing left to do obviously is to do a real world test. And the only way to do that is to turn a machine on. So everything is currently set up to ensure ultimate success. So we've got our gate closed, closed, open, open, open. So what we should be seeing in this video or this section is we should be seeing the gate open, this gate close, this gate open, and these two gates close, and then the dust collector needs to turn on. So let's hope, fingers crossed, that everything is going to work. So, our 4 and 5 are closed, our 1 and 2 are switched, and our gate number 3 is now open. So, thumbs up so far, that's working. So the next thing to do is to turn the machine off, and what should happen is that after a 3-second delay, the gate should close, and the dust collector should switch off. So that delay we can obviously tweak, but it's designed to obviously clear out the system. So, let's make sure that that's working. So power is off, we're waiting 3 seconds, gate's closing, and our power is switched off to our dust collector. So, I don't know about you, but that's extremely promising. So now that we've seen the system in action and it appears to be working well, the obvious next question is, well, what next? We certainly can't call this mission accomplished just yet. Like any system that mixes electronics, moving parts, software, we're going to need some real world time in the workshop to see how this is going to perform over a longer period of time. And I envision there's probably going to be some tweaks and small improvements along the way. I already have a few small areas I'd like to try and tidy up, but the main thing is that the core elements are all there and we can build and improve upon it. One idea I have been floating is that if this particular prototype system proves reliable, how hard or expensive would it actually be to get a custom PCB or custom shield made that includes all the components on a single PCB? A unified PCB would certainly make the electronics a lot simpler. It would mean that people could simply buy it off the shelf and integrate it into the systems that they build within their workshop. Now, we're a long way from doing anything like that, but let me know in the comments below if that's something you might be interested in the future. One of the best things about this whole project has been listening to your feedback, your thoughts, your queries, your comments, your questions, and obviously your own guidance and advice. It's actually really helped me guide where this project is going, and I encourage you to keep doing that. So if you have ideas for features, improvements, or even completely different approaches to certain things, then let me know. Put a comment in below, or even send me a message or an email. I always respond to emails and I genuinely love your feedback. Now, before we wrap up, there's one more thing I'm sure a lot of you will be curious about, and that's the cost. Now, the costs I'm about to show only relate to the electronics I used in the system. They're not going to include the cost of actually printing or building the ball gates themselves. But at least should give you a rough idea of what's involved if you are planning to do something similar. Now, of course, there are probably some savings to be had if you're buying components in bulk, or if you're able to source alternative parts cheaper than I did. And all of the components used in this build either come from Amazon, AliExpress, eBay, and a local supplier here in Australia called Core Electronics. And with that, that basically ends today's video. A huge thank you once again, as always, to my channel members. Without your support, I cannot work on projects like this, so your generosity is hugely appreciated. So thank you to my newest members, Clay, Craig, Brad, and Wood Chronicles. And welcome to the paddock. Thanks for watching, and I'll see you again soon.